Okay, welcome to electrical machine lecture. Now continue with the previous topic, that is losses and efficiency of DC motor. So this is the numerical. A 6-pole 500 volt wave connected shunt motor has 1200 armature conductor and useful flux per pole is 20 milliweber. The armature and field resistances are 0.5 and 250 ohm respectively. What will be the speed and torque developed by the motor when it draws 20 ampere from the supply main? Neglect armature reaction. If the magnetic and mechanical losses amount to 900 watt, estimate useful torque, output in kilowatt and efficiency. So now we will proceed with the given data. It is given that the number of pole P is equal to 6. It is wave connected motor. So therefore A is equal to 2, whereas supply voltage 500 volt and number of conductors Z is equal to 1200 armature conductors. Useful flux phi per pole, it is 20 into 10 raised to minus 3 Weber. It is from milliweber to Weber. The armature and field resistances, armature resistance RA equals to 0.5 ohm, whereas the shunt field resistance RSH is equal to 250 ohm respectively. What will be the speed and the torque? Means we are going to calculate the speed. N is equal to how much? And the useful torque developed by the motor when it is draws the load current I is equal to 20, at which we want to calculate uh, torque and speed. And the next is, whereas the mechanical losses, magnetic and mechanical losses, that is WC constant losses is equal to 900 watt. So this much data is given. So for the DC shunt motor, it is better to calculate the shunt field current first. So ISH is equal to 500 divided by 250. So it is 2 ampere shunt field current. And hence the armature current IA, it is a motor. So I minus ISH. So it is, we want to calculate at 20 ampere. So 20 minus 2, it is 18 ampere is the armature current at which we want to calculate the different data. Now the total number of conductor is given and the current is armature current is given. So we can calculate the back EMF. So it is EB is equal to V minus IA RA, which is equal to 500 is the voltage minus 18 ampere multiplied by 0.5. So it is 491 volt. Now we know the formula of back EMF EB is equal to pi Zn upon 60 into P by A. So everything is given and already we have calculated the back EMF. So back EMF is 491 is equal to 20 into 10 raised to minus 3 into 1200 is the number of conductor. Speed we want to calculate divided by 60 into number of pole is 6 and A is the number of parallel path as it is wave connected. Hence, speed n is equal to 410 rpm. So this is the speed that is calculated. Okay. Now, what is the next? We want to calculate the torque developed by motor. So TA, torque developed by motor, TA is equal to 9.55 into back EMF into armature current divided by speed. So it is EB is equal to 9.55 into back EMF 491 into current is armature current is 18 ampere divided by 410. So here the torque, armature torque equals to 206 Newton meter. So this is the armature torque. It's torque developed by motor. Torque developed by motor. Now we want to calculate the efficiency. We want to calculate useful torque. So for the useful torque, it is necessary to calculate the power output. So here the power output, first we will calculate the motor input. Motor input is equal to V into I. So it is a 500 volt multiplied by the 20 ampere. Since the 20 ampere is the total current drawn by motor, it is the total current drawn by motor including the armature current. So this is the 20 ampere. This is 18 ampere. Now it is 2 ampere and this is the voltage is 500 volt. This is the case. So total input is 10,000 watt. Now if we calculate the losses in the armature circuit and shunt field circuit, so Cu loss or armature Cu loss is equal to Ia square Ra. So it is 18 square multiplied by resistance 0.5. So the copper losses is 162 watt. Similarly, shunt field Cu loss, it is equal to 500. Okay, we'll write one more step. That is voltage into ISH equals to 500 multiplied by 2. So it is 1000 watt. Magnetic and mechanical loss, as it is already given, it is 900 watt. So in this way, the total loss is equal to 162 plus 1000 plus 900 equals to 2062 watt. Now the power motor output. Total losses we know. So we can calculate the motor output. Motor output is equal to motor input minus total losses, and it is comes 7,938 watt. So now the power output we know. So we can calculate the useful torque TSH is equal to 9.55 into 7,938 divided by the speed of motor, it's 410, and therefore TSH is equal to 184.8 Newton meter. Now see, the torque developed by motor, that is the armature torque, it is 206, whereas the shaft torque or useful torque is 184, which is smaller. It means that there is a power loss in the DC motor. So mechanical losses over this one. So in this case, we can calculate now the efficiency. So this is the data we want to calculate. So this is the data. Now efficiency. Percentage efficiency is equal to 7,938, whereas the motor input is 10,000 watt into 100. So the efficiency of motor equals to 79.36%. So this is the parameter at given data. Now the second numerical, a 50 HP 37.3 kilowatt 400 volt DC shunt motor is running light, taking a current of 4 ampere and runs at speed 600 rpm. The resistance of armature circuit is 3 ohm including the brushes, and the shunt field resistance is 270 ohm. Determine when the motor running at full load, current input, speed, and determine the current at which the efficiency is maximum or efficiency will be maximum. So this is so here uh, we will start calculating. First, we will calculate the shunt field current. So it is 400 volt is the supply voltage, and shunt field current is 270. So it is 1.7 ampere is the shunt field current. Now shunt field CU loss. Shunt field CU loss is equal to resistance and voltage, or voltage and current in the series shunt field winding. It is 1.7. So it is 783 watt. This is the shunt field CU loss. Now first is the running at no load condition, or here it is given as a running light. Light means it is at light load condition or running at no load condition. So what is the armature current? IA is equal to I minus ISH. So the no load current is 4 ampere minus, this is the no load current. So no load armature current, it is 1 minus 1.7. So it is equal to 2.3 ampere. So it is the no load current. So now no load armature Cu loss is equal to 1.7 square into it is a 3.2.3. So armature current is 2.3 bracket square multiplied by zero point 0.5. It is a 3 ohm. It is the resistance is zero point 0.3. It is the resistance is 0.3. So it is 0.3 ohm and it comes around 1.5 watt. So it is very negligible. So no load input, no load armature input 460 multiplied by 2.3. So 400 and this is 460. Okay. So 460 multiplied by 4.3 ampere. So it is 1058 watt. This is the armature input. Copper copper losses in the no load condition is very small. Hence, uh, it can be neglected. Now, let it is given that the frictional and windage losses, which will be assumed to be constant. So we will consider that let full load current, full load armature current is IA. It is we are assuming. Then we can calculate armature input, armature input equals to voltage, rated voltage 400 and into IA, which is equal to 460 into IA. Similarly, armature Cu loss, it is written as IA square RA. So it is IA square into zero point 0.3 and rearranging it is a 0.3 into IA square, and output of motor, output of motor already it is given. It is 50 HP or 37.3 kilowatt. So 37,300 watt and it is given. Now from the power stages, we can say that the motor input is equal to motor output plus constant losses. Yeah, constant losses plus armature Cu loss. So as per this one, motor input is nothing but V into Ia is the motor input. Then motor output is 37,300 watt plus constant losses is 10. This is 1058 plus armature Cu loss, which is zero point 0.3 Ia square. Now, if we rearrange the equation, then it is 0 0.3 Ia square minus 460 into Ia, means we have putting the value of this one, plus the addition of these two, 38,358 equals to 0. So it is the quadratic equation, and by solving the quadratic equation, we come to know the value of Ia in the two values. So the permissible value, it is 88.5 ampere. So once we know the current, that current is the armature current. Therefore, first part is the current input. So which is equal to, say, I, it is Ia plus ISH. So the value of current is 88.5 plus 1.7 equals to 90.2 ampere. So this is the first point. Now second is the speed we want to know. So first we will calculate the back EMF. EB is equal to V minus Ia Ra. So no load condition, and EB at load condition V minus Ia Ra. So here it is 460 minus the armature current at no load condition is 2.3 into 0.5, whereas it is 460 minus armature current, it is 88.5 into 0.3. So the back EMF in the two cases, EB0 at no load condition, it is 459.3 volt, whereas for the load condition, it is 433.5 volt. So now N upon N0 at no load condition equals to EB upon EB0. So therefore the speed N is equal to 660 multiplied by, it is 433.5 divided by 459.3. So the speed is equal to 624 RPM. So this is the speed and this is the current. So these are the two values. Now what is remaining? Maximum current, the armature current at maximum value of efficiency. So third point is current corresponding to maximum efficiency. So for the DC machine, the maximum efficiency when when variable loss become equal to the constant loss. So here the variable loss is the copper losses in the armature. So IA under the maximum condition, IA maximum efficiency square into the resistance 0.3. What is the constant losses? It is already calculated. The losses which is going to occur into the shunt field and as well as the uh, constant losses which is given, which is already calculated from the no load input. So it is 1058 plus 783. So this is the total constant losses. And from this one, armature current at maximum well efficiency is 78.33 ampere. So this is current corresponding to current under maximum efficiency. So this is the uh, few numericals based on the efficiency and losses. So thank you for listening.